Okay, in this one, we're going to be looking at, instead of, for the last one, we had the conical shape. You know, the sand is falling into a shape of a cone off of the conveyor belts. In this case, we have a sphere that's increasing. Okay, so if we look at everything that we know, the radius is increasing or changing at 3 inches per minute. So if we look at what that entails, that means that the change in the radius with respect to time, that's 3. Okay, and then part A says find the rates of change of the volume. So we want to know the change in volume with respect to time. So it's very important to identify that right off the bat. That's what we want to know. And then also, this is two-part question. Part A is asking, okay, how fast is the volume changing when the radius is 9? Part B, how fast is it changing when the radius is 36? So let's go ahead and solve this. Since it's the rates of change of the volume of a sphere, that is what the equation we're going to be using that relates to the change in the radius and change in volume. So it's going to be 4/3 pi r to pi r cubed. And then when we differentiate that, it's dv over dt, because it's with respect to time. And the derivative of just v is 1, so you could put a 1 times that there. And then you would bring this 3 down, because r is your variable there, pi is a constant. So it's going to be 4 times 3 over 3 times pi times r squared. And those 3's will cancel, so we can rewrite dv dt as just 4 pi r squared. Okay, so that's the relationship between the change in volume and the time. So now, whoops, I forgot this. Since it's changing, let's come back here. Since it's changing with respect to time, not the radius, we need to include this. Otherwise, it'd be dr over dr, which is 1 anyway. So it's got to be dr over dt. My bad. And so when we simplify that, that would be dv over dt, 4 pi r squared, dr dt. Now that's the equation that we're going to be using to answer both parts A and B. So in A, dv dt is 4 pi times 9 squared times 3, which gives us 972. Let me move over a little bit. So that's 972 cubic inches per minute. And part B, our change in volume with respect to time, is 4 pi times now 36 squared times 3. And that is 15,552 pi, and that's inches cubed per minute as well. Okay, so those are our two answers. This one when the radius is 9, and this one when the radius is 36. And it makes sense because if it's always changing 3 inches per minute, the bigger the balloon gets, the faster the air is going to have to go in. So because it gets larger and larger and larger, the radius is getting larger, so the faster the volume is going to change as well. Going to have to change to make up for that. All right, so let's take a look at B. It says explain why the rates of change of the volume of the sphere is not constant, even though dr dt is constant. Now, we just kind of talked about that. You can draw pictures to talk about it, whatever you want to do, but it's a problem of proportionality, right? If you look at the change in the volume, that was represented back here, 4 pi r squared. So the change in volume is not a constant proportion. It's actually a squared proportion, okay? And so that means it's the change in volume is going to be changing a lot faster depending on the radius. And we already know what the radius is, the change in the radius. Oops, dr dt. That was 3. Okay, so for example, if you have a balloon this size versus a balloon at this size, the radius is still changing at 3 inches, what is 3 inches per minute. and then 3 inches per minute here, even 1 inch change here, the change in volume is so much greater than 1 inch change here. So that's why the change in volume is not constant, even though the change in the radius is. Here we have a boat being pulled into a dock by means of a winch 12 feet above the deck. So let's draw this and kind of see what shape we're looking at. So here's the dock. Here's the boat, my beautiful boat. Here's some waves. And here's the winch, and it's pulling in. So you can kind of see the shape we're looking at right here is a triangle. So chances are we're going to be using equations that deal with triangles. Could be areas of triangles, could be side lengths of triangles. Now let's read the rest of the problem. It says the winch, so first of all, the boat's pulled in. So we know that the dock is 12 feet, or sorry, the winch is 12 feet above. So let's go ahead and label that. So the winch pulls in a rope at a rate of 4 feet per second. Okay, so the rope, so let's say that this is Z. Okay, that changes at a rate of 4 feet per second. So that means the change in the rope length over the change in time is -4. Because it's getting shorter, it's a negative change. That was this right here. Determine the speed of the boat when there is 13 feet of rope out. So now we know that Z then is 13. So this is Z. We know that it's 13 and that its rate, it's being pulled in at 4 feet per second. Okay, then it goes, so we can answer that, but then it says, what happens to the speed of the boat as it gets closer to the dock? So let's answer the first question, right? So we have a right triangle, and we're looking at side lengths. So we know we're going to be using the a squared plus b squared equals c squared. But instead of a, b, and c, I'm going to say that this is x, this is y, and here we have, whoops, it's a terrible z, here we have z. All right, so it's going to be x squared plus y squared equals z squared. If any of these are constants, you can put them in. And in fact, x is a constant, right? Because that's 12 squared. But y is changing and z is changing. Y is the distance from the boat to the dock, and z is the length of that rope. They're both changing, so we leave them like this. This is the equation that tells us the lengths of all of these sides, one being a constant. And we find the derivative to tell us how they are relating to each other in their change. And so we're going to find 2y, and that's times dy dt, 2z dz dt. All right, now if we look at all of the variables at this time that we already know, and this is 0 here because this is a constant. If we look at the variables that we already know, right, we know that z is 13, and dz dt, the change in the rope, it's being pulled in by that winch at 4 feet per second. And then over here, we do not know dy dt. We do know y. It's implicitly given to us because y is that third side. So if you know a squared plus b squared equals c squared, you know that this is 12 squared plus y squared equals 13 squared. Y in this case has to be 5. Okay, so it's going to be 2 times 5 times dy dt, and you know that we're going to divide out that 2 times 5, and I leave it as 2 times 5 because you can more easily see that those are going to cancel each other out. 2 and 5, 2 and 5. So you'd have dy dt is equal to 13 times -4 all over 5, which simplifies to -10.4, and there that changes feet per second because that is how quickly that boat is being pulled in. So that's the change in that distance from the boat to the dock. in terms of seconds. Okay, and then that second part, what happens to the speed of the boat as it gets closer to the dock? Well, you can test that, right? You can go ahead and put in a different value. So if it gets closer to the dock, let's go down here. An example would be, so instead of this being 13, let this be 9. Okay, this would be 12, and we can figure out what that third side is going to be. Can't be 9, obviously, because the dock itself is 12, and it actually pulled the boat up. So let's try 12.25. So if that's 12.25, then this has to be 3.5. Okay, so when we set this up, x squared plus y squared equals z squared. Remember, this is our only constant, so that 12 will always be 12. Oops, plus. That 12 will always be 12, and so when we find the derivative again, we're going to get something very similar. dy dt is equal to 2z dz dt, and we plug stuff in. And if we remember, well, the y, we know what the y is going to be. That's 3.5. We don't know what the dy dt is. The z is, instead of 13, it's 12.25. It's pulled in a little bit. And the dz dt is still -4. And we go ahead and divide each side by the 2 times 3.5. The 2's will cancel. And you end up getting -49 over 3.5, which simplifies down to just -14. Okay, so then it was, remember, this is compared to the -10.4 feet per second that we got up here. I'll highlight it there. Now it's -14. So that tells us it's actually being pulled in faster as it gets closer to the dock. So it gets pulled in faster. There we go. You can read it. Okay, as it approaches the dock, the speed of the boat gets faster and faster. So let's take a look at this next one. I want you to read it, try this one on your own, and then come back to the video and we'll go over it. Make sure you have tried this on your own before you come back, or if you need a little bit of help setting it up, look at this. It's a triangle problem, changing in side lengths. It's just asking about the change of a different side lengths this time, because the boat is moving at a constant rate at 4 feet per second versus the rope itself. So what that tells us is, instead of dz, the change in the rope, it's the change in the distance from the boat to the dock. That is what's changing at 4 feet per second, and it's a negative because that distance is getting shorter. So if you need to, pause the video and try it on your own. Point, we're going to go ahead and plug in all of our knowns. 13, and again, a squared plus b squared equals c squared. That's how I find that missing variable, which is 5 for y, but we did that on the last problem as well. And then we're going to divide out that 2 times 13. Those will cancel. And then you'll have dz dt, the change. In this case, it wants to know the change in the speed of the rope. The change in the speed of the rope, or that distance in the rope, how fast is it being pulled in, is -20 over 13. Here, let me write it on this other side. -20 over 13, and that's in feet per second. And that follow-up question, what happens to the speed at which the winch pulls the rope in? Well, it's going to be opposite of the other one, because the winch is actually going to have to slow down if it wants to keep the boat at a constant rate of 4 feet per second. So the winch is actually going to have to slow down in this case. And again, you could prove that by finding a different length. So like when the boat is 2 feet closer, so this y then would be 2. You could look at that and kind of determine what to prove that would be true.